to another exciting episode of Everyone's a Winner, the game show where we see if strings will be accepted by a specific regular expression. I'm your host, Mac. For our new viewers, this is a show where we take a regular expression and translate it into a non-deterministic finite automaton, or NFA, and then a deterministic finite automaton, or DFA, and then our contestants, which are strings of characters, see if they are accepted or not. This week, our celebrity regular expression is, open parentheses, A or B, close parentheses, star. As our fans know, every week we start by translating our regular expression into an NFA. So let's begin. First, let's make state 1. This is where we will begin. You'll note that our regular expression this week is a simple OR statement followed by a clean star. This means any number of repetitions of what's within the parentheses, even 0 repetitions, and the star comes first in order of operations. So, since a total lack of input is within the language of this regular expression, let's go ahead and make this starting state accepted. There. Now that that's out of the way, let's look at our possible outputs. If you input an A, what does it look like will happen? Well, that would be one valid iteration of the OR statement, leaving us right back where we still are. So let's loop the input back to our starting state. Now, how about B? Well, that is also a valid iteration of the OR statement, so let's add B to this loop. Well, that's that. We have every possible output from every conceivable state, and we have empty edges for every conceivable condition that would result in an automatic failure. That would be none. Our NFA is completed. Time to turn it into a DFA. Turning an NFA into a DFA isn't very complicated. Let's begin. Step 1 is to make a new state for every possible combination of current states. This is because a string in an NFA can exist in multiple states at a time, but strings in a DFA must be in a single state at any given time. Remember, any combination state which includes an accepted state is itself an accepted state. Some people like to do that step at the end, but I prefer to do it here. In this case, let's look at every possible combination of our single state. And that was pretty easy. Alright, next we make a reject state. This is where we'll put everything in the NFA that was an automatic failure when would lead. Our next step is to check every edge. Anything that leads to multiple states, we move into one of the relevant combined states. Okay, now that that's done, we look for every state that doesn't have an output for either A or B and send that to the reject state. Well, we don't need to send anything from the reject state because anything there is automatically rejected no matter what. So we're done there. Finally, we eliminate any of our new states that weren't used. There aren't any combination states to eliminate, so it looks like we're just getting rid of the reject state. And there you have it. The DFA for the regular expression, open parentheses, A or B, close parentheses, clean star. Now, this is the simplest way to convert it into a DFA, but the truth is, we could construct the NFA to be arbitrarily complex. There could be dozens of states. There could be hundreds of states. You could have a nigh endless chain of states where A and B either loop or lead to a new state at essentially random. Since this expression accepts literally all strings, any DFA will work as long as one condition is met. Every single state has to be an accepted state. Once that's true, any proper DFA will fit this regular expression. The only way one could fail would be if it did something crazy, like having a state without all the proper output edges. And it's not that much more complicated to make an infinite number of NFAs representing this string. You just need every state to be accepted, like the DFA, and also you need to make sure there's an edge for every possible output from each state. Within those two conditions, literally any NFA will work. Add epsilon edges, don't add epsilon edges, it doesn't matter. Either way, it works. Well, enough chit-chat. It's time for the game. Let's bring in those strings and see which of them are accepted and which aren't. First, we have AB, AA, B. Let's step up to the state and try your luck. Alright, we start in our only state. Going through the string, first we have an A, which loops back to the starting state. So does the first B. Then the next A does the same thing, as well as the following A. And finally, the last character, a B, our second one, also loops back to the starting state. We have a winner! Congratulations, man! You just won big on Everyone's a Winner! Okay, let's bring in our next contestant. What's this? The empty set. Well, sir, I am a big, big fan, huge admirer of yours. It's a pleasure to meet you. Let's try your luck. Okay, the empty set begins in our first and only state. Then it does nothing and goes nowhere. Bold move, sir. Bold indeed. And he's a winner! The clean star allows for 0 repetitions, so the empty set is a success. And now, let's give a big welcome to our last contestant. Oh my. Okay, well, that is quite the entrance. Let's try to cram our new contestant in here. Okay, well, I'm not going to actually try to list this whole string, but we know that our starting state treats A's and B's exactly the same. So all we need to know is that the string has 68 characters, and that each of them is either an A or a B. Let's see what happens when a string of 68 random A's and B's are fed into our DFA. Wow! Would you look at that? Another winner! I guess that's why they call the show Everyone's a Winner! Thank you for playing. You've all been wonderful. Now as ever, we'd like to end our day by having a serious talk about complementary languages. They are the exact opposite of what we work with here on Everyone's a Winner. You see, every expression accepts some inputs and rejects others. Each expression's complement, therefore, is the expression that is the yin to its yang, accepting everything it rejects and rejecting everything it accepts. From our DFA here, we can easily deduce the opposite. All you need to do is flip the accept status of every state. In this case, we go from a single state accepting everything to a single state rejecting everything. You see, it turns out the complementary language of open parentheses A or B close parentheses star is an empty set, which is somewhat ironic, since as we just showed you, the empty set itself is accepted by today's expression. The complement doesn't even accept that. It really makes you think. On that note, my stage manager is giving me the wrap, so it's time for us to move on. Promotional consideration for today's programming brought to you by Jorg Kraus. Thank you, Jorg. Stay tuned to this channel. After a brief commercial break, we'll be back with breaking news from the Binary Information team.